So today we're going to talk about networking. Ironically, like I said, we are having a networking issue in the classroom. So we're going to try to make this a learning experience because you're going to come across this problem in the real world. And you're going to have either your kids or yourself wondering what the hell's going on, and you think the internet's down. Well, let's declare what is the internet and how it might not be the internet being down. It might not even be your connection to the internet, but it might be something on your network. So first of all, what is a network? Oh, I got to get some new markers. That works. So what is a network? A network is two or more devices connected together to share resources. That definition has a lot of vague terminology. Two or more devices. What is a device? This printer is considered a device. It is a networked printer. Your PC is considered a device. Tablets, laptops, your television, your Blu-ray player, all today are considered devices. How do they connect together? Sometimes through a cable called the Cat5 Ethernet cable. Sometimes via airwaves. Other times through coax. Instead of calling it a connection, we tend to use those as a term called a medium or media. So what are resources? Resources could be files. They could be currency. They could be games. They could be movies, songs, web pages, Facebook statuses. The point is that we connect multiple devices together to share. That printer is a resource on our network. I bought one printer and I want to share it with everybody. Our internet connection could be considered a resource. So how do we make a network? Well, the elements of a network, so this is the definition of a network, the elements or components, you're going to need at least a sender. You're going to need also somebody else to receive this. Remember, two or more devices connected together. So one device is going to be a sender. The other device is going to be the receiver. You're going to need a message. Usually that message is carried by a signal. And that signal is going to be distributed or sent via medium. And because we have senders and receivers trying to pass messages to each other, we need to have some kind of rule or protocol that's going to govern the structure of the message, the language of the message. We take this for granted because in this country we've been indoctrinated into the English language. So when we meet somebody, we assume that they speak English, so we talk in that language. We make this giant assumption. I don't ask you guys before I start class, is there anybody in this class that doesn't speak English? I make that assumption. Computers cannot make assumptions. Before they actually start transmitting messages to each other, they have to agree on a protocol. One of the most popular protocols, and you might have seen it, is called IP or IPv4. The I stands for Internet, The P stands for protocol. Today we're going to explore what the IP protocol dictates and how does it set up a method for transferring messages back and forth. So a network are two or more devices connected together to share resources. To create a network, you're going to need a sender/receiver. One being, now that role will switch back and forth. Messages, that could be the resource itself or the request for the resource. The medium to carry the message, as well as the protocols. So what I like to do is create a topology. You can think of topologies as being a blueprint of a network. And we have two forms of topologies. We have the physical topology and we have the logical topology. The logical topology basically gives you an illustration on how the network behaves. For instance, a ring topology, one would think it'd be like a circle. And if I were to hook up a device, now in networking terms, we call this a node. Now that's only one device, right? Do I have a network? No. Let's get another device. So now I have a network. Two or more devices connected together to share resources. So let's call this node 2. We'll call this node 1. If node 1 wants to ask node 2 if they have a particular file, it's asking for a resource, it's going to send a message. Which direction would the message travel? Yep, from 1 to 2. How's it going to get there? Around the ring. Does it matter which direction it goes? Okay, so it could either go this way or it could go that way. But eventually the message should get to that device, correct? Let's put a node in here. And let's put another one over here. Now node 1 still wants to talk to node 2. Remember, it could go left or right. This is just the logical behavior. Let's just say when node 1 and anyone goes to talk around this ring, traffic will flow in a clockwise fashion. Think about those roundabouts. Like we have a roundabout out here at the center of our entrance, Connect Corning. Do you see how there's only one lane there? So we got to make sure that the traffic all follows that direction. It doesn't matter if people are going left or right, but as long as they're all going in that same general direction, correct? Could you imagine if some dipshit decides to go opposite direction as everybody else is going around that roundabout? What's going to happen? An accident. In networking, we call that a collision. Okay? So no two devices on the same medium can send and receive at the same time. You clear about that? So think about sending and receiving as going in opposite directions. So when node 1 wants to talk to node 2, what's going to happen with the other communication going on in this network? It's going to stop. They're going to listen. In fact, how does node 4 or 3 know that it's their time to talk? How do you know it's your time to merge into that roundabout traffic in this center of our entranceway? When there's enough room to fit your car in front of somebody without pissing them off, correct? So there's some kind of visual cue. In this network, that visual cue is known as a token. In fact, we typically call this a token ring. You could think of it as a microphone or a mail cart in a corporate office that gets passed from desk to desk to desk. Right now, node 1 has the microphone, and it wants to communicate with node 2. In order to get there, it's first going to go to node 4. Node 4 gets the message. But the message is not assigned to... So we have, this is coming from node 1, and it's going to node 2. Node 4 does not have the address that matches this destination. In other words, you get the mail carts being passed around, see what's inside of it, and it says, this is addressed to Mitch. If you're not Mitch, what are you going to do with the letter? Pass it on. Node 4 is not node 2, so it's going to pass the message on. You see this little relay going on from device to device? The important thing, the thing that should concern yourself, is maybe security. Node 4 decides to not open it up. What makes that determination is this protocol. It's a set of rules. And in there it's going to say if the destination IP address of this message does not match your address, ignore it. In fact, we get into a physical address, if you will. Case in point is the message is now being touched by node 4, determines it's not that, pass it on to node 2. Node 2 gets the message. What is it going to do? So this token's being passed around. Node 2 sees that this message was destined to node 2. That's me. What would you do if a message came by and had your name on it? Open it up. In the meantime, none of these other devices can communicate with each other. Even if node 3 wanted to have a conversation with node 1, that wasn't going to happen. Why not? The only time you're allowed to communicate in this network is when you have the microphone, the token. Where's the token at right now? At node 2. This is a logical behavior. Why do we do it this way? Why do we have roundabouts versus stop signs versus traffic lights versus intersections without any kind of control? And that's the key here. This is called media control. What do you guys prefer? Intersections without any control. Traffic lights over stop signs over roundabouts. Over in Europe, they're all about the roundabouts. In this country, we're all about the intersections with stop signs or traffic lights. Let's talk about it. Which one's more effective? No control, stop signs, traffic lights, or roundabouts? Traffic lights? Traffic lights is almost like this. When you have the green light, you can go. When you have the red light, you can stop. So traffic lights are good for like large volumes, correct? But it's 1 o'clock in the morning on Denison Highway. Nobody's around, and I have a red light. And I'm waiting, and waiting, and waiting, and waiting for it to go green. Yeah, exactly. Especially near the Dunker Knife. Now, what about stop signs? Everybody has to stop, right? But it's like a 1 at a turn, so it's like 4 seconds, go. I know, it's just people are rude. So what about roundabouts? How does roundabouts work? They're yields. So if there's nobody there, you can just keep on going, correct? And if there's somebody in the circle, then you have to stop or at least slow down so they can get ahead of you. The idea in a roundabout is you keep the traffic going, moving. The problem is that people always try to think they have the right of way when they're the one trying to merge into it. Oh, in the cities, they get really horrible because there's more traffic, right? So this is what I'm trying to say. The more users we have on the network, what's going to happen to the number of messages we have? The more chances of an accident, correct? We want to try to avoid that. Why do we want to try to avoid these collisions? Think about it. When there's an accident downtown in a busy intersection, what is that about? What does that mean about your traveling experience? Delayed. And that's what happens to your network. The more users you have on your network, the greater the chance that you're going to have collisions. The greater the chance you have a collision, the poorer performance becomes. Right? This is one method to handle it. We say, look, shut up until you have the microphone. And what does that mean about collisions? As long as everybody's following the protocols, 0 collisions. Right? That means large amounts of data can be distributed. That's one philosophy. This is a logical layout. It's not actually wired this way. It just allows us to understand that if you're at this point and you want to talk to this one, you're going to go in this direction. That means you're going to be going through, stopping at these points, and they're going to be checking the information out. Now, there's another way of doing it. We'll call this a bus. In certain network terminology, it's called a multi-access topology. I like multi-access topology. It's a lot better than calling it a bus, but nevertheless, it's still the same thing in general. There is a common medium here. It's this backbone. By the way, this is the way coax television works. And if you have broadband from Time Warner, this is going to be a similar technique and how they manage it. Generally, in these topologies, they implement something called CSMA/CD. The CD is that collision detection. Any one of these nodes can communicate at any time. But before they go to communicate, they check the medium to see if there's a carrier, the signal that carries the message. If there is no signal, then it's safe to do what? And isn't that the way we communicate in this classroom, if you will? What is this carrier, or what is the medium in this classroom? What do you and I use to transmit back and forth? Can't do it in space. There's an old movie made in the late 70s, and their movie poster used to say you can't scream in space, or nobody can hear you scream in space. And the physics behind that is there's no air in space. And if there's no air, not that you can't breathe, is that you can't transmit. Because look how we talk. Suck in a bunch of air. You vibrate your vocal cords. The air comes out in your mouth as a message now, as a signal. Your eardrum detects the varying pressures that your vocal cords created, correct? Well, if there's no air to breathe in to carry the message, then you can't talk. So we use air to communicate with each other. And when the air is silent or dead, what does that mean you can do? This is your opportunity. If it's quiet, what can you do? Talk, right? And that's what happens here. What's cool about that is it doesn't go around in here. If this person doesn't have anything to say, they're going to get the microphone, and then they have to pass it. You can talk when you want to talk as long as nobody is using the medium. Does that make sense? Now, what happens from time to time, like when 1 and 3 want to both talk, and they both check the medium to see if the signal is available. It happens in this classroom. I'm waiting. It's dead air. It's your opportunity to answer once again. This is the protocol that we have to establish. Most of you guys don't raise your hand. Some of you do, and I call on that. They're raising their hands like a token. But here I'm just saying, well, if I'm not talking, it's your opportunity to talk. And what if both of you, or more than one of you, if you will, wants to say something? You listen, the air is dead, and you both transmit. And then there's a collision, correct? How do you know there's a collision? Because while you're talking, you can also listen, right? We call that full duplex. In this network, we have full duplex. Well, let's not do that yet. I'll modify that. We have half duplex. And the reason why I'll modify it is because the next topology, I'll say we have full duplex. If full duplex allows you to talk and listen at the same time, then half duplex means like CB radios. You push the button to talk, you let go of the button to listen. We good about that? I say this is half duplex because if 3 is transmitting to 2, 2 is listening. Nobody else can talk right now. Likewise, while I'm talking, you guys are listening and nobody else should be talking because it can be disruptive. Now, if there's a collision and 2 people are talking at the same time, whether you detect it or somebody else is going to detect it, they're going to make it a big announcement. Like I did at our meeting on Tuesday. Shut up, right? That's called the jamming signal. So like I said, this type of topology uses something called CSMA/CD. Carrier sense, multiple access. I have more than one nodes accessing the same medium. Collision detection. This one doesn't try to prevent collisions. It just says, look, Nick, if it's 1 o'clock in the morning and nobody's around and you checked both ways, go ahead and cross the red light. Should I worry about a collision if there's nobody around? For miles? It's 1 o'clock in the morning. I do have a red light. The protocol says to me, stop, wait to go green. This type of technology is saying, well, look, nobody's using it. Go ahead and cross. So, we don't avoid collisions. We just build the protocols to accept them and communicate. And if there is a collision, try to clear out the wires. Obviously, the more people on this network, slower it becomes. This one scales really nice because there's no collisions. So we can have a lot of people on large geographical distances. Here, small graphical distances, smaller sets of people. So what do we do to make the best one? Whoops, not that. Star. So you guys are thinking something like this. Right? Remember, these are all logical topologies. I'm using them as tools to illustrate how the message travels or behaves on these types of networks. In the center of a star topology is going to be a switch. And radiating out from that switch are going to be nodes. These are like points to a star. Between the switch and the node, we have what we call a logical point-to-point network. Point-to-point. It's actually point-to-point protocol. It's usually PPPP. I mean 3 Ps. And then let me do that so I don't get point-to-point protocol. What does that mean? If this is the only device or devices connected, what does that mean about collisions? If it's only you and somebody else, there shouldn't be any, right? If you're just going out with a friend and you're having a conversation, They talk, you listen, they stop, you talk, they listen, right? If it's more than two, then you might have a problem because now you might want to talk, but the other person wants to talk too. So you got to worry about collision. So here we don't have collisions. We love these types of networks because we gain what we call full duplex. Why? Because the switch acts like a way station. It's like Grand Central Station. Everything comes and goes to the switch. The switch has a big buffer. It builds it up. When this port becomes available, or when this node is able to listen, the switch will pass the message through. So you send everything to this center device, and it distributes it for you. This is like back in the day when we didn't have traffic lights or stop signs, and we had traffic cops. And they would stand in the middle, and they would wave people on, and they were smart enough to detect when there was going to be a collision, if you will. Here, we drop it all in here, and the switch passes it around. Star topology supports full duplex. The nice thing about star topologies, and this is the way you typically wire your home networks, if you want to add another device to your network, you simply plug it into a free port and hook it up to your computer. Done. On this network, you have to crack or cut the line. When you cut that line, it brings the whole network down. Because at the end of these, we have what we call terminators. To let them know that the signal doesn't propagate too far out. Because remember, the signal's constantly going through these wires, so we got to terminate the signals. In order to add to this, we got to cut the network, bring it down, add the device, and come up. This becomes a problem with troubleshooting. You don't know where the problem might be on the wire, so you got to use some fancy tools to try to narrow it down, then splice it. And the problem of fixing it, you bring the whole network down. Here, if this computer is experiencing a problem and no other computers are experiencing a problem, I might just check the cable between here or there, the port, or just that computer. What about something like this? If it goes down right there, is communication lost? What if we just switch directions? Is communication still lost? When you send something, you better get a message back. Can we send the message back? Because we have to travel in this direction if we're using half duplex. That is, if the medium that we're using only allows it to go one way, and we decide to switch it and pass it this way, I can't back it up that way. But wait a minute. Nobody should be talking while I'm trying to have a conversation with this device. So yes, it's called a sonic ring, and we can bounce it back. Now, if this happens, the only people that can have a conversation is 1 and 3 and 2 and 4. Does that make sense? Where are these topologies used? Connect cities together. Connect homes together, maybe, depending if you're using coax and cable TV. Connect homes. Connect local devices. Now, folks, this is just a general overview. Of course, it gets more technical than what you're seeing now, but this is just a literacy course. You don't have to be experts in networking, but I want to make sure that you understand that each of these topologies have their own way of managing the message. Okay. I like to start small. I like to start at our house. Remember, we're experiencing some technical problems, and we need to try to narrow it down. This classroom is an example of a star network. In fact, this classroom is called a local area network. short for a LAN. Once again, we're back to a generic word. What do we mean by local? If I ask you, is anybody local to Corning? What do I mean by that? You live in the Corning area? So, if I say this classroom's example of a local area network, what do I reference it? What am I trying to specify here? Everything's close together, so it's a very small geographical location, the scope. This classroom is one local area network. The classroom behind this wall is another local area network. It becomes tricky on how we define it. One aspect is a local area network is governed or controlled or administered by a single organization. Your home would typically be a single local area network, and you're responsible for the devices that connect to your network. Okay? Geographical space or size. Let's compare your home network to a corporation or even to this classroom. Does anybody have more than 18 devices on their home network? We have 18 devices, if not more, here in this classroom. Now you go to compare it to a big corporation, they might have thousands of computers. So local is very tricky. I like to define it as it's a small network organized by a single individual organization that have a common interest, goal, or resources. Case in point, we meet in this classroom to talk about 1390. So this class, in a sense, is like a local area network. We want to exchange ideas, resources. People are networks. You guys are a device, I'm a device. We are connected together by air. You have some knowledge, I have knowledge. We share that. That's the definition of a network. When I define a local area network, I'm focusing on the Ethernet standard. A lot of people call this an Ethernet cable. We're going to give it a better name in a minute. The Ethernet standard dictates the type of interface we will use to get onto the network. In fact, that has a better name. It's called a network interface card. The Ethernet standard also states that we're going to be using IP addresses to identify each node. Hence, it basically says as a sub-bullet, no two devices on the same network can have the same IP address. Why would that be a problem? Why would it be a problem that two devices on the same network have the same IP address? Bless you. When we send messages to devices, we use IP addresses to identify them. So if there are two devices on the same network that have the same IP address, the device that's responsible for relaying the message around won't know which one to send it to. Do you mean Nick or do you mean Nick? So hence, all devices have to be unique. This is a good area to troubleshoot. One, you need to make sure that your devices on your network has an IP address. If it doesn't have an IP address, then how am I supposed to send you something if you don't have a name or a mailing address? Second, these IP addresses are going to have something known as a network address and a host address. So it has two parts. You can think of it as your name. You have a first name and a last name. Your last name, for the most part, is shared with other people in your family, correct? Doesn't that sort of identify your group? Well, on an IP address, certain parts of the address is shared by other devices to help define what a local area network is. What else does it define? The type of medium that's going to be used. Why does this become important? When you guys buy a USB flash drive, are you worried about it not plugging into your computer? Why not? Why aren't you worried when you buy a USB flash drive that it will not plug into your computer? The fact that it says USB flash drive. If I tell you if you buy a Thunderbolt flash drive, should you then be worried? So that's why we say you need to have an Ethernet card. You need to have an Ethernet cable, and you need to have an Ethernet switch. They all begin with the word Ethernet, so they should be compliant. And Ethernet comes in many different flavors or speeds. We have 10 base T, 100 base TX, 1,000 base, I believe it's T as well. What are they referring to? You've seen that before, right, folks? Capital M, what does that typically mean? Mega, right? Lowercase b, what does that mean? Be careful, lowercase. What's that, Mitch? Bits. This is where your telephone or your internet service provider gets you all the time. Because what's bigger, bits or bytes? In other words, what's going to take, when you write it on a piece of paper, how many bits make up a letter? Nice little review. 8, right? Which we call a byte. So when you compare 1 byte to 8 bits, you think 8's a bigger number, correct? So this gives you a larger number, but when you go to compare it to bytes, technically it would be smaller. Translation, this is about 1 megabyte per second. If you have a 5 megabyte song, it would take you 5 seconds to transfer this file. Okay? This is about 10 megabytes per second. Therefore, this would be about 100. I'm just dividing by 10 because I took the 8 and rounded it up. You guys get the general philosophy here? So be careful of that. So what's the PS then? And it's not postscript. Per second. So we are measuring literally how fast it takes bits to travel through this particular network. Local networks have huge amounts of bandwidth. Now you have to be careful. Bandwidth has 3 sort of classifications. You have what we call the nominal or theoretical bandwidth, the throughput, and the good put. Marketing people use the biggest number out of that. That would be the theoretical bandwidth. You will never obtain the theoretical bandwidth. Never. It's like the miles per gallon in a car. If it says 35, you're probably never going to get 35. Right? So then you got this throughput. The data plus the overhead. Because I have to send address information plus other things to tell the network how to handle this packet. I called it a message earlier. Now I'm calling it a packet. A packet is just a little sliver of the message. So the good bandwidth, or the good throughput, is just how fast the data, the stuff that you care about, is transferred. And it's usually about 80%, 70 to 80% of whatever your actual bandwidth is. Okay? So if you are having Time Warner as your broadband company, by the way, other factors in Paris too, right? Number of users. But if they're your bandwidth or your broadband company, they sell you a 10 megabit per second, just multiply that by 80%. And that's about, give or take, what you should expect to get. Okay? So, to build this local area network, I'm going to need a switch. A switch is an intermediary device that handles local traffic. They give us full duplex, and they negate collisions. You're going to need either twisted pair, Ethernet cable as you guys are commonly referred to, and a network interface card on your end device. Your switch has ports. Now remember, 2 or more devices connected together. These interface cards are the ones that get IP addresses. How do I know they're on the same network? Because they're connected by this device here. They're in the same physical network because they're using a switch. Since I'm using the Ethernet standard, I'm using at least Cat5 twisted pair cable. You could think of this as just glorified telephone cable. If I were to cut this open and expose the pairs for you, what you would see is a bunch of wires wrapped around each other, hence the word twisted. Now they come as pairs. Why? The biggest hurdle in offering consumers broadband in this country is the distances. We're a very wide country. I think we're about 3,500 miles wide. Anytime you deal with length and physical properties, you're going to get resistance. It's like putting your car in neutral and rolling down a hill. Without starting it up or doing anything, eventually your car will come to a stop, correct? You have the resistance, the internal resistance plus the external resistance. Likewise here. This is a copper cable. What does copper carry very well? And why do we use it? What do computers use quite a bit? How do we manipulate data in computers? Electricity, right? So when I go to transmit the message from computer to computer over this twisted pair cable, I'm going to be using electricity. And as with anything, there's going to be resistance in here, and there's also going to be interference. Because when you run electricity over a copper wire, you are going to generate what we call an EMF, electromagnetic field. Electromagnetic, it's electromagnetic, right? What do magnets use? What do they love? What attracts them to the other? They align, north and south poles, right? So basically, if you will, the polarity or the electrons on one material is being grabbed by the other material, by the other magnet. Folks, what carries electricity? Electrons. So therefore, we can say that our electrons are carrying our message, right? So if I am sending voltage this way through this cable, I'm generating a magnetic field that goes around. Here's the issue. That magnetic field is going to be messing around with the other pairs. We all right with that? Hence it causes interference. To negate this interference, we take the opposite direction, the sending pair. And so it's pointing in this direction. We wrap the magnetic field around there and they cancel each other out. This cable's very cheap because of that. We're not adding layers of insulation or aluminum foil to protect it. We're just taking 2 copper wires, wrapping them around each other and sending electricity in opposite directions. Economical. It's great for running it in your house. It's like maybe a cent a foot if you buy it in bulk. Extremely fast, very dependable. Very safe. Not as safe as fiber, but safer than airwaves. But yes, folks, you do have to run the wires to connect your devices to your switch. What do we do when we don't want to do that, though? What do you guys go and buy? A wireless router? Now you'll notice that our wireless routers become integrated. That is, they take the switch and they integrate it into that device. You can look in the back of your wireless router and you'll see a bunch of ports. And Ethernet's all good with that. In fact, what do we call this? It's 802 dot. 802 dot is the Ethernet standard. And then you guys have 11. It might be A, B, G, N, and now we're up to AC. And what are they telling me by using those letters? A, B, G, N, A, C. Which one's better? A or AC or N or G? They tell you distances. And that's important when you're in Wi-Fi, right? You want to know how far you can travel in your house. Just like a dog testing his boundary when he's on a leash. And the other thing that becomes important is if you are starting to distribute high-definition content across your local area network, you need bandwidth. Out of those, B is the slowest. Then we go to GA. I always go between G and A because A uses a 5 gigahertz spectrum and G uses a 2.4. G uses a very common spectrum, hence a lot of interference. A doesn't, but it uses a sensitive frequency. So it's a give-take relationship. So I always like to rank A and G, depending on your environment, the same. So what about N and AC? N can handle bandwidth up to about 300, this is not counting multiple outs, about 300 megabits per second, okay? AC is 1 gigabit per second wireless. It's the new standard. I think it was released last June. I think it's like $300 for the router and $100 for the interface card right now. But if you're distributing high-definition content across your wireless network, or you're trying to share resources between your neighbors' computers, and they're in another building, AC is the way to go. It's a lot more powerful. How do you know this? Just go to the store, look at the router box, flip it over, they'll tell you what the transmission rates are. Okay? The point is, this is an Ethernet wireless router. That means this wireless router can hook to my switch, which means it's compliant with our network. Which also means if I have a laptop, what am I up to, node 3? Connected via the airwaves, what must that laptop have? Wi-Fi card, or interface card. And that interface card must have what? All of these nodes must have a similar IP address. But two can't have the same IP address, right? What do I mean by a similar IP address? When you go to set the properties of IPv4, your computer is going to ask for the node's address. I'm just going to do the standard. Have you guys seen that number before? When you've had to set up your wireless router in your house, like a 192.168.1, or maybe 192.168.254, or something to the effect. And then there's going to be another number. I'll just start off with 1. An IPv4 address is 32 bits. Translation, it contains 4 parts. Right? What's 32 divided by 4? 8, right? How many bits are in a byte? Getting the connection now? Each of these parts are 8 bits. Now, what's 2 raised to 8? I know it's been a while. What do you need to know? These numbers can only go from 0 to 255 per each of those. When you are configuring a computer and you say, well, you know what? Let's use 368. It's not going to work. Your operating system will yell at you because each of these octets will only allow you to enter a number from 0 to 255. And for most part, 0 and 255 are reserved. So technically you go from 1 to 254. We clear about that? So when you go to set an IP address up on your network, make sure it's within this range. I don't care what it is. You could say that I want 1.2.3.4. And I will check, this is where the protocol comes in, that each of these octets are between 0 and 255. Is it? All right. The next thing. How do I determine if this computer's IP address is 1.2.3.4? What do I make this computer's IP address? Should I do 2.2.3.4? Because the next number after 1 is what? How does somebody know I have one of those unfortunate names where my first name and my last name could be a first name? Right? How does somebody know that it's my last name and not my first name? How do we identify that? What usually comes first in professionally printed documents? That's usually in the phone book, right? Last name first in the phone book, but like when you write a letter, dear, you might put a Mr. in there, or if you're going to spell out the full name, what comes first? First name, right? Hence the word first name. Okay. When it comes to an IP address, our computers need to know what we call a subnet mask. Usually it's specified by default. Have you guys seen that before? When you're typing in an IP address on one of your devices, you just click on the subnet mask box and it automatically puts in like the 255s. This is what you need to know as far as what determines this. This is the network address. How do you know that? What did appear underneath each of those octets, each of those numbers? 255s, right? So I'm saying any number with a 255 underneath it is part of the network address. We okay? So what's this part then? We call it the host. That's what needs to be unique. So when I go to give this computer an IP address, it needs to be 1.2.3 because they're part of the same local area network, right? So if they're part of the same physical network, they also need to be the same logical network. Now, what can I not give this computer? 4, because 4 is used by the other computer, correct? So let's give it a 5. Now let me give this computer an IP address. 1.2.3.6. Does this need an IP address? Has anybody secured their wireless routers? How did you do that? Okay, how did you set the password up? Did you open up a web browser? And in the address bar, did you type in the IP address of your wireless router? Unless it came with the CD, which would have done the same thing for you. Okay? I know that the newer wireless routers are becoming smarter, but this should get an IP address. It's going to have dual functions, if you will. Notice I gave it a 1. Now I said it's going to have dual function. This is it. This is a network. Everybody has an IP address. No two devices on the same network have the same IP address. They are all connected together through some medium, whether it's twisted pair or wireless. And they're using the same standard. Can I expect a lot from this network? Not really. The only thing I can expect to share on this network is whatever local files I have stored or local resources. If I add a printer, I can share that. As long as that printer has an Ethernet card and I properly configure it so that no two devices have the same IP address, it can be shared. What else could I share on this network? You know what? Maybe I want to take one of my older computers and make it into a server. If I'm going to make it into a server, it's going to need an IP address. So I'm going to give it 1.2.3.3. What is that server going to do for me? I know I'm a home user, and I'm getting a little carried away, but my biggest problem is that I have a bunch of files scattered all over my network. So-and-so has pictures. So-and-so has the videos of the family picnic. If their computer crashes, I lose those memories. Unless they decided to back it up on their own external hard drive or a flash drive. But how often do we back up our files? We don't. So if I had a server or some external network area storage device that does that, I can set this server to back up all my devices on my network at a certain time. If these computers are stationary, if I'm downstairs in the living room and I want to check a particular file out, whether it's my taxes or grade papers or whatever, and then all of a sudden I want to go upstairs because the weather's nice and I want to look outside the window, by having all my files stored in a centrally located area, wherever I go in my house, I should be able to access them. Translation: the server's running all the time, and they give the people to share resources in what we call a client-server relationship. Something you guys are familiar with using the web. Correct? This technology is going to be implemented in your household. I don't believe you guys will be having full-blown computers. I think you might buy one massive computer, if you will, and that these nodes are simply going to be monitors that allow you to talk and touch. That gives you your I/O, right? All the processing, all the storage will be done here. What does that mean as far as growth, scalability? Yeah, I'd be concerned about putting all my Easter eggs in one basket, but if it's just here, all I have to do is get a new monitor, a new keyboard. I can keep on adding to the network low cost, especially if it's a Wi-Fi network. So my question is, how do I make this network be able to do more, share more, or have access to more resources? What must we do, and why must we do this? It's not a requirement yet, but it sure is a necessity we can't live without. Or a necessity that we can't live without. If I want this network, if you will, to share more resources, or have access to more resources, what must I do? Remember, it's a local area network, local to my house. It can only share resources that are contained within my house. If you guys want to go to California, what must you do? Get off your ass, jump in your car, and do what? Leave your driveway and connect to an interconnected highway system that we call the interstates, correct? Now, do you pay every time you get on that road? Not per mile, but your taxes pay for that road, correct? Okay, so what you're saying is we need a pathway that connects us to a bunch of other networks. Whoops. Around the world. And that's what we call the internet. The interconnected networks, or networks of networks. They probably have switches, and off of their switches, they probably have little devices. Oops. This is called a wide area network. You see, it just gets on wider and wider. And if I want to talk to so-and-so over here, my message will first go to my router, depending on what type of connection I have to my, what's the word I'm looking for? 3 letters. Your ISP. Your ISP probably connects to other ISPs, which we call NSPs, network service providers. So this is just one example of how a wide area network is just a sliver of the whole internet. So we have a router that serves the purpose of being able to pass messages out of our network onto other networks. Another word for your router is called a gateway. It's like the door to this classroom. This is a local area network. That hallway is a wide area network. Why? What does that hallway do? What does it connect? Other classrooms. And didn't I say the other classrooms would represent their own networks? And so somewhere on those other networks is a resource that I'm looking for, whether it be Google, whether it be Yahoo or Amazon. And so my message now travels from my network to all these other networks until it finds its final destination. What does that mean about all the devices that are connected together? What should they have? What have we learned when we create a network? They all must have IP addresses. What does the I stand for in IP? Internet, right? All of these devices must have an IP address. Well, my question is, at home, if you guys told me that you're using 192.168.1.1, how can I use that? What's this? Yes. This is a local area network, and it's protected, if you will, by my ISP. In fact, when you probably order broadband to your house, by the way, I'm not talking about dial-ups, even though they follow a similar nature, probably get a modem. Familiar with this? It's usually a black box that your cable comes into or your telephone line comes into. And all the modem is short for modulate, demodulate. Translation, folks, we got these signals. Right now, the type of signal that's traveling through this is the Ethernet signal. But now I need to switch it over to my cable company. Right? They use coax, which is going to use a different type of signal. And it's going to have a different way of modulating the message. So that I have to have a modem to basically modulate the 2 different ways, sort of acting like a bridge to connect the 2, if you will. So the router serves 2 purposes. It's designed to protect your network, like your door in your house, because your door in your house has a lock, correct? Your router will have what we call a firewall. And also be natted. This becomes very critical. Because we are getting to the point where we have stuff at home that we want to be able to access from anywhere and around the world. Or our firewall is designed to close up ports, connections coming and going from our computer. If we haven't initiated the conversation, then nothing can come in through that hole, if you will. So the firewall basically inspects the packets that are coming and going, and if we haven't asked for that packet, in other words, if you're not invited into my party, what's my front door man going to do? Turn you right around, because you're not on the list. That's the firewall. What about NAT? Network Address Translation. It takes your private IP addresses and converts it into a single public IP address. When you order a monthly subscription from your ISP, they give you a public IP address. Let's just say I better not use one, let me use 2. And that's going to be on this side of your wireless router. Folks, when you buy your wireless routers and you configure them, you notice in the back there's certain ports that are identified uniquely. It used to be called the WAN port. What's it called now? Thank God they did this. Usually you'll have 4 ports to plug in for wired network, for wired devices. But then you'll have one special port. Got a little globe on it. The internet port, right? That's the port you would hook up your modem to. You good about that? That port is literally the gateway out of your network. So when these other computers want to talk to you on your network, they use this external IP address, your public IP address. Okay? Then it comes to that router. That router looks at it and says, oh yeah, so-and-so made that request. You see this point? You as a client make the request. Google just doesn't go pounding on your door saying, here, you want this. No, you must first type in a domain name in your web browser. By doing that, you make a request. Now wait a minute. I said in order to pass messages around, we use IP addresses. But when we type in to our computer, more importantly, into our web browser, do we type in numbers? No, we type in domains. We've learned about domains, right, and all the different parts of it. So, how does the computer use the name to communicate on a network that requires numbers? By the way, this is the problem that we're having in our lab today. It's called DNS, Domain Name Services. And this is what we're going to do together as a class, taking this theory and making it practical, because I needed to cover these components so that we can look at the physical world and narrow down what's causing our issue. First thing, if you walk into a building or in a room and you try flipping the switch and the lights don't come on, what's going through your mind? Build this troubleshooting method. Do you have a blown light? That's a possibility, right? What else could be a possibility? Okay. What could cause the power to be out? Storm? You didn't pay your bill? An accident? What's in your control, though? Anything that's local, correct? So what you might do is look across the road and see if your neighbors have power, if their lights are on, right? What does that rule out? Somebody hit a pole, or the storm knocked out the power, unless they have a generator. So be very thorough, knock on your neighbor's door, and say, do you guys have power? If yes, are you running a generator? All right. No. So that means I know at least we have power going up our road. Now, do you inconvenience your neighbor before you do your own system check? So you flip on the switch, nothing's going on, Maybe you go to another room. What do you do there? Nothing comes on. What are you thinking now? All right, so first step, you go to a computer on your network. You check internally. Doesn't work? Jump off of that computer, go to another computer. Doesn't work. Now you're going to check your circuit panel. Now these are those little black switches. They flip sometimes automatically if there's a surge. So you check to see if they're all flipped on. They are. Now what's the problem? What's the next thing you're going to check if the circuit panel is working? None of the lights come on in your house. You guys are going to be faced with this, right? What are you going to do? Maybe you didn't pay your bill. Maybe your transformer out and your pole's blown. But that's beyond the stuff that you could have checked, correct? So let's do this. I want everybody to hold your window key. And hit the letter R. Type in CMD. Are you guys faced with a black screen with white text? This is called your command prompt. Remember when we were learning operating systems, I said something along the lines that we have a graphical user interface and we also have a command line interface. I love using the command line interface to troubleshoot networks. The first thing we check is the self. We call this a loop back ping. I want you guys to type in PING space 127.0.0.1. Now, I probably got a little ahead of myself, and I probably should have had you guys check something before you do that. But when you guys do that, I'm just trying to get my monitor up. Not able to sign in? Oh, check the cable back behind it. Is it? All right. All right, so you guys have this screen right here, right? So when you held the window key and hit the R, and you typed in CMD, and then hit enter, this screen pops up. All right, like I said, this is your command prompt. The first thing we're going to do is we're going to ping our loopback. So I'm going to type in PING space 127.0.0.1. What do I test, or what am I testing when I do this ping? Your operating system goes through you, the user, interacts with the operating system, and then it interacts with the software. But the software has to interact with the hardware, right? So we have this stack, these 7 layers that the message has to go through. Just think of them as like little checklists, if you will. What the loopback does is it just checks to see if this stack is functioning properly. I haven't even left the computer at this point. So if this loopback fails, there's something wrong with this, and you have to reinstall your network driver. Okay? That address works for everybody. 127.0.0.1 works on all devices that have an Ethernet card. Okay? You know it worked because you get a reply from. Okay? You see the time it took to get back to you is less than a millisecond? Because all you're saying is, self, are you still there? So you're going down through the stack, checking to make sure the protocols are functioning. The next thing you need to do is ping your IP address. How do you know what your IP address is? Well, we have a command. It's called IP, ironically, config, or conveniently. So all one word, type in IP config and hit enter. It's going to list all the interfaces on your computer that have an IP address. Do you see we have an IP address v4 of 192.168.1, then dot something? Everybody else has a number there? We all have. Dan, you're saying no? Oh. Yeah, I'm getting to the point that's causing the issue. I am working up the ladder. But those who are able to log in, 192.168.1, then some number afterward, right? Nobody in this classroom should have 220. You good about that? You notice you have the subnet mask of 255.255.255.0. I know that everybody in this classroom who has that subnet mask will have the first three octets of the IP address the same. You good about that? And then everybody in this class has a 192.168.1.1 for the gateway? No. Interesting. What do you have, Josh? Nothing. You can use the computer, we can communicate with each other, but what can't you guys do? Alright. But some of you guys don't. What is the gateway? It's the way out. If you don't have a door and you're in a room, guess what you can't do? Leave that room. Right? So we might have some issues with connectivity, but let's ping ourselves. So let's ping our IP address of 192.168.1.220, or whatever your address is. What that tests is your interface card and the cable connected to it. Now, I like to rule that cable connected to it, because in a minute, we're going to ping your neighbors. Did you guys get all replies for all those that could do this? Good. Ping your neighbor. Find out what their IP address is. So somebody give me an IP address. Vanessa, what's yours? .218. Alright, so Vanessa gave me her address. Now what am I doing here? I'm testing to see if I can connect to my switch and her connection to the switch is good. Because isn't that what connects all these local devices together? So if I get replies, which I do, I have local connectivity, correct? So, step 1, loop back. Step 2, ping your IP address. Step 3, ping your neighbor's IP address. You guys have the same IP address? What have we learned, though? Two devices on the same network can't have the same IP address, so therefore that's probably why you didn't get a gateway address, because if it was automatically assigned, they didn't know who should get that address. So we have a conflict there because we have duplication. Next thing, I'm going to ping my gateway address. So I'm going to ping 192.168.1.1. What a ping does is it sends the message to the device, to the door, and then it comes back to me if I get replies. If I don't get replies, guess what's going to happen? I have a problem between my switch and my router. Do you see how it's like an all or nothing test? Alright. I'm able to communicate with my gateway. I like this. So far, so good. Everything's working. Now I need to ping an external computer. A computer on another network. But see, I don't know what their IP address is. But what I do know might be their domain name. So I'm going to ping Google. So I ping www.google.com and I hit enter. And it's taken a lot longer than it did before, right? And it's going to fail. What does the computer need? What does the ping command need at this moment in order to communicate with Google? Google's IP address, right? What service on our network is responsible for taking a domain name and resolving it into an IP address? DNS. My DNS server is down. You see, it's a server. What have we learned about servers? Many people connect to it. You see, we all had a problem earlier logging into these computers because we're all logging into the same server. So when I try this, I'm at the server now. I want you guys to open up your web browser. And I want you guys to type in the following IP address. Type in 173.194.43.14. And tell me if Google's, well, it won't work for you guys because you guys don't have a gateway. Tell me if Google's webpage comes up. So open up Firefox or Chrome and type in 173.194.43.14. Did Google come up? It should have. What happened is I said, let's not use the service and let's dial the number directly, right? I'm able to get right to it. So that tells me as a technician, I'm having a problem with my DNS. At this moment, if this was your house, you would call your ISP up and saying, there's something wrong with my domain name services. It's on them. Okay, folks? So we'll finish this up on Tuesday. You guys have a good weekend. PowerPoint assignment has been posted on my IT lab. We're only doing 2 parts of access. Okay, guys? You guys take care, and I will see you on Tuesday.